Swayam Prabha. Digital India. Educated India.
Lecture 6 in this series is a short overview of disturbances of plasma pH. Plasma pH is the negative logarithm of its free hydrogen ion concentration. This proton concentration is at 40 nanoequivalents per liter, and that is what keeps the plasma or extracellular fluid pH at 7.4. The major determinant of plasma pH is the ratio of bicarbonate and carbon dioxide. As per Henderson-Hasselbalch equation, pH is pK plus log bicarbonate by carbon dioxide concentrations. Bicarbonate in plasma is at 24 milliequivalents per liter and carbon dioxide is at 1.2 millimoles per liter. Therefore, the ratio is 20, and that is what keeps the pH at 7.4. Any change in the concentrations of carbon dioxide and bicarbonate can disturb the plasma pH. What are the possibilities? An increase in carbon dioxide or a decrease in bicarbonate will lead to acidosis, whereas an increase in bicarbonate or a decrease in carbon dioxide will lead to alkalosis. Let us consider broad mechanisms which could lead to each of these disorders. Let us take up an increase in carbon dioxide, acidosis due to an increase in carbon dioxide in plasma. The sources of carbon dioxide coming into plasma are what comes from the tissues, and carbon dioxide formed from fixed acid protons consuming the bicarbonate. These are the sources of carbon dioxide, whereas the sink for carbon dioxide is uptake by red blood cells and removal via the lungs. These are the sources, and that is the sink. The question now is increase in carbon dioxide brought about by increased formation from the sources? The answer is no, because whatever be the carbon dioxide that is formed from these sources, if the removal system is normal, then whatever is formed can be adequately handled. So, increased formation of carbon dioxide is never a cause for increase in plasma carbon dioxide. The only cause for an increase in plasma carbon dioxide is when the removal mechanism is inadequate. Where is the inadequacy? Could red blood cells be a cause for inadequate removal of carbon dioxide? Say, if there is anemia, not enough red blood cells or not enough hemoglobin, could that be a cause for inadequate clearance of plasma carbon dioxide? Not really, because even in anemic conditions, there is enough hemoglobin to buffer the carbon dioxide. That leaves us with the lungs as the only cause for inadequate removal of carbon dioxide from plasma. Ventilatory failure, hypoventilation or inadequate ventilation is the one and only cause of increase in plasma carbon dioxide. Therefore, acidosis resulting from an increase in plasma carbon dioxide is termed respiratory acidosis. The same holds good for a reduction in carbon dioxide in plasma. Any reduction in carbon dioxide in arterial blood is only due to hyperventilation in the lungs, where the lungs are blowing away more carbon dioxide than is formed in the tissues. And therefore, alkalosis or an increase in plasma pH due to a reduction in plasma carbon dioxide is termed respiratory alkalosis. We will now consider changes in plasma pH due to changes in bicarbonate. A reduction in bicarbonate causes acidosis, and what could be the probable causes of a reduction in bicarbonate? Some of the causes are obvious from the arrows shown here, some are less obvious. We will discuss them in detail as we go, but for now let us follow the arrows. a decrease in bicarbonate could come up either due to reduced formation in the kidney, reduced reabsorption in the proximal tubule, or reduced generation in the distal tubule, or the bicarbonate concentration can reduce because of increased consumption by the fixed acid protons. Which of these is a real cause for reduction in plasma bicarbonate? The answer is all of them. A reduction in plasma bicarbonate is termed metabolic acidosis. The term came up probably because one primary cause of a reduction in plasma bicarbonate is due to consumption by the fixed acid protons, and the fixed acids are formed due to metabolic processes. That's why probably this term metabolic acidosis has come to describe all conditions where there is a reduction in plasma bicarbonate. But notice that decreased formation of bicarbonate in the kidney is also classified under metabolic acidosis. A special term to refer to those conditions where there is a reduced formation in the kidneys is renal tubular acidosis, either proximal renal tubular acidosis or distal renal tubular acidosis. However, all of these are classified under the term metabolic acidosis. So, the term metabolic refers to a change in bicarbonate concentration. Similarly, an increase in plasma bicarbonate, the causes can be renal or gastrointestinal causes. However, all these conditions are classified under the term metabolic alkalosis. So, it is important for us to realize that whether there is any metabolic cause or not, any change in bicarbonate in plasma is classified under metabolic. A decrease in bicarbonate is metabolic acidosis, and an increase in bicarbonate is metabolic alkalosis. These are the 4 conditions that we will discuss in detail in the subsequent lectures. The message is primary changes in carbon dioxide concentration is called respiratory, and primary changes in bicarbonate concentration is termed as metabolic. Now, let us take up respiratory acidosis again. When there is an increase in arterial carbon dioxide because of hypoventilation, the only way to set it right would be to improve ventilation somehow. However, in the interim, till ventilation could be improved and the plasma carbon dioxide can be blown out, there must be temporary mechanisms of pH correction even though carbon dioxide is higher, because enzymes require that narrow range of pH. So, an increase in carbon dioxide can be compensated for by a corresponding increase in bicarbonate so that the ratio does not change and remains 20. And that happens when carbon dioxide increases in plasma, the kidneys increase generation of bicarbonate so as to keep the ratio at 20 and maintain the pH from changing too much. We have referred to increase in bicarbonate as metabolic alkalosis. Therefore, when you see this increase in bicarbonate, some books refer to this condition as compensatory metabolic alkalosis or secondary metabolic alkalosis. I would prefer to use the term renal compensation for respiratory acidosis. Similarly, when there is a respiratory alkalosis, the kidneys will eliminate some bicarbonate and reduce the bicarbonate concentration so as to maintain pH. There will be a compensatory or secondary metabolic acidosis. I would still prefer to use the term renal compensation for respiratory alkalosis. In metabolic conditions, that is, if there is metabolic acidosis due to some reason and bicarbonate is decreased, now the lungs will blow out more carbon dioxide and keep carbon dioxide concentrations low so as to maintain pH. So, in metabolic conditions, there will be respiratory compensation. Some books again would refer to this as secondary respiratory alkalosis, secondary to metabolic acidosis. In metabolic alkalosis, primary metabolic alkalosis, where the plasma bicarbonate has increased due to some reason, again temporary maintenance of pH will be brought about by the lungs withholding some carbon dioxide and increasing carbon dioxide concentration in plasma. This can be thought of as respiratory compensation for metabolic alkalosis. We have now seen 4 major classes of pH disorders and compensatory mechanisms thereof. The lungs compensating for metabolic conditions and the kidneys compensating for respiratory conditions. Let's see them all together. These are the 4 classes of pH disorders we will be discussing in the subsequent lectures. The primary disturbances is in white arrows. In respiratory acidosis, it is an increase in carbon dioxide. In respiratory alkalosis, it is a decrease in carbon dioxide. In metabolic acidosis and alkalosis, the change is in serum bicarbonate. The compensatory mechanisms will be shown in green arrows. So there is renal compensation in respiratory conditions and respiratory compensation in metabolic conditions. You would notice that in respiratory acidosis and metabolic alkalosis, both acid and base have increased. So how would you know whether it is a primary respiratory acidosis or a primary metabolic alkalosis? pH will tell you what it would be. Even though there is compensation, it's almost always an undercompensation. Therefore, when the pH is low, you know that this condition has to be an acidosis and therefore a respiratory acidosis. If pH is higher, this has to be an alkalosis and therefore it has to be a metabolic alkalosis. These 2 conditions have the same profile in terms of carbon dioxide and bicarbonate concentration, and again the giveaway will be the pH. The pH is going to be different in these 2 conditions. We will see more of this in the lectures that will come up. Thank you.